So in this video, what we're going to do is we're going to learn a technique of integration that allows us to combine some of the rules we learned from previous parts on integration and antiderivatives to some more complicated examples. So section 4.5, u-Substitution. In this case, sometimes in your book, this is called integration by substitution. Okay. So the idea here is that we're going to be looking for a certain form of the integrand when we take an integral. And if it is in a certain form, then we're going to be able to, in some cases, take the antiderivative of it. So let's say, for instance, we have something called the integral of 2x e to the x squared dx. Okay, and so in this case, what we have is we have a composition of functions. So when I take e to the x squared, like we talked about before with the composition of functions and the chain rule, the exponent here is x squared, but the outer function is e to the something. So the something in this case is x squared, so that's the inner function, and e to the something is the outer function. So what we're going to be looking for is, in general, there's a few cases where we'll look for something slightly different, is a function of a function, and then we're looking for the derivative of the inner function on the main line. So if I call this x squared my inner function, because it's the inside of a function, then its derivative appears here on the main line as 2x. So what we can do is we can do what's called a u-Substitution. So what we're going to do is we're going to say u is equal to x squared. All right, and then what we do is if u is equal to x squared, so this is going to be our inner function, then we can say du dx equals 2x, and so du equals 2x dx. Okay, and so what we see on the main line of the integral is we see 2x dx, which we can substitute du for because it's 2x dx. And then when we have e to the x squared, that's just going to end up becoming e to the u. So now I can rewrite this integral as e to the u du. And if you remember, when we were looking at integrals before, we said e to the x dx is equal to e to the x plus c. Here we have e to the u du is equal to e to the u plus c. And so what we want to do is we want to substitute back in for u because we made up u, call it a dummy variable. So we get e to the x squared plus c as our final answer. So in this case, we would say this here is the integral of 2x e to the x squared dx. All right, and so what we might be interested in doing is checking for what this answer is and see if the answer is correct. So if we're saying that this here is the antiderivative, then if we take the derivative of this, we should end up getting this expression here, which is in the integrand. So let's say I do d dx of e to the x squared plus c. This is equal to d dx of e to the x squared plus d dx of c. All right, and if you remember, we have this chain rule for d dx of e to the x squared, where we take the function and write it again, and then we multiply that by the derivative of the exponent, which in this case is 2x. So we have 2x e to the x squared. And then the derivative of a constant is going to be 0. So what we see here is that this checks. All right, and we don't have to do the check, but it's helpful when doing antiderivatives when you first start to check it and see if it works out. Okay, so let's look at a few other examples of u-Substitution. And again, the idea is we're looking for a function of a function for the cases that we'll be doing in this class, and then we're looking for the derivative of the inner function to appear on the main line of the integral. So let's say that I have something like this. I have the integral of x squared minus 2x plus 4 to the 5th power, and that's times 2x minus 2 dx. Okay, so in this case what we have is, again, we can see that we have a function of a function. So here we have something that's like the power rule, but that's a power function, but the inner function is this polynomial x squared minus 2x plus 4. And then we can see that if I call u is equal to x squared minus 2x plus 4, then I can say that du dx is equal to, in this case, 2x minus 2. And so du is equal to 2x minus 2 times dx. All right, and so again, here we have a function of a function, and then we see that the derivative of the function appears, the inner function appears on the main line. So now what I can do is I can rewrite this as u to the 5th, and 2x minus 2 dx, which appears in the integral, we're saying is now du. So then this ends up equaling, using the power rule for anti-differentiation, 1/6 u to the 6 plus c. And then we can plug back in for u. So we have x squared minus 2x plus 4 to the 6th power, and that's going to be plus c. So basically what we're doing in this case is we're undoing the extended power rule, because now if I took the derivative of this part right here, the 6 would come down in front, multiply the 1/6, and so that would give us a 1. And then we'd have this inner function, x squared minus 2x plus 4, all raised to the 5th power. We'd have to multiply that by the derivative of the inner function, which in this case is 2x minus 2. And that would give us what's in our integrand, and the derivative of c, of course, would be 0. So this is another example of how we can use the extended power, or the integration by substitution, to solve for some of these integrals. So let's look at one more case of this in this video. So let's say that we have something like the integral of 2x dx over 1 plus x squared. All right, so in this case what I'm going to do is, I see that I have a fraction, essentially I have a function divided by a function with the dx on top. And in this case what I see is that the derivative of the denominator, which is 2x, appears on the main line of the integral here. All right, so what we're going to do is we're going to end up saying, in this case, that u is equal to 1 plus x squared. All right, and then if I take du dx, that's equal to 2x, and so du equals 2x dx. All right, so if I do this, the integral of 2x dx, that part becomes du, because I solved for it over here. And then this here is divided by 1 plus x squared, which we're saying is u. All right, so we have something that's like u to the negative 1, or 1 over u. And we know that the rule is that that's going to be the natural log. And if u is greater than 0, that's going to be the natural log of u. And if u is not greater than 0, then we're going to do the natural log of the absolute value of x, where u does not equal 0. So in this case, what I'm going to do is, if I have u is equal to 1 plus x squared, that's going to be always positive, because 1 plus x squared is always positive. So this is going to end up being the natural log of u plus c. All right, and in this case, again, we do have a function of a function. We have the inner function is 1 plus x squared, and then the outer function in this case would be 1 over x, or 1 over u. And so we took the inner function and call that u, which is 1 plus x squared. And then we took du dx is equal to 2x, and so du equals 2x dx. And then we see that that appears on the main line of the integral, so that we can call our du. And then we can apply the rules that we know, which is that the integral of 1 over x dx is equal to the natural log of x plus c when x is greater than 0. So here our final step would be to take the natural log of 1 plus x squared and then add c to that. Okay, so in the next video I'm going to show you another case of u-Substitution that's slightly different, but basically this is a good foundation for working on the problems that will appear on this week's quiz.